Hi everyone, it's Miss G again. Thank you for being so flexible with me being gone. I appreciate you all. It's a new week. Hopefully, I sound a little bit better than I did last week. Um, but I should be able to see whoever will be in class on Wednesday. I'll be in that day. Um, but, anyways, so welcome. We are going to finish up the lesson on atoms from last class period. So, if you remember, we were talking about kind of like the history of who discovered the atom. We talked about the parts of an atom. We then we then talked about atomic number and atomic mass. You were supposed to have filled in the worksheet. It was called Atomic Mass and Atomic Number Worksheet. That was due last week. I can open it up for you if you are still finishing it. Today, we're going to move forward with still atoms. Okay, we're still not completing this big overarching objective of atoms, molecules, and bonds. We're taking it a step further on and hopefully reaching out to bonds soon. Or I'm sorry, like coming to the point where we'll be able to talk about bonds as soon as we finish up with atoms. So, specifically talking about atoms, today's objective is that you'll be able to model electron configurations based on atomic number. And you really can't talk about bonds until you get this part of it down, modeling electron configurations. So that is going to be important. Okay, so kind of thinking back on some of the rules that we learned last class or in the last video, can atoms have different numbers of protons and electrons? So kind of pause the video there, figure that out. I would look at your notes. Oops, not this one. I would look at your notes for atomic number and the rule about atoms being neutral. But go ahead and write that down in your notebook. Make sure you pause the video and write all of this down. This is a continuation of the last lesson, so it could be the same page. Okay. So I'm not going to give you the answer to that. We'll talk about it in class, but it's in the PowerPoint before. Okay, so last time I introduced you to the periodic table, and I said that each little element on the periodic table has a symbol. So, for example, hydrogen is symbolized by H. It has an atomic number of 1, an atomic mass of 1.008. If I went over to nitrogen, nitrogen has an atomic number of 7, an atomic mass of 14.007. It's symbolized by an N. Now, so hopefully you get the drift of that at this point, but elements are really represented by these little squares, okay? And if you haven't already written down kind of like what or where everything is on an element box, then you can do that now. So, for example, the element symbol is always going to be letters. Okay, so for example, calcium is signified by Ca, and the first letter is always going to be capitalized. Okay, the second letter is always going to be lowercase. So for example, calcium, I can find on the periodic table. It's going to be right here. Okay. For instance, titanium, notice again, it's a capital letter and then a lowercase letter. Only 2 letters. And it's not always going to be the first 2 letters of its name. For example, like gold, gold is symbolized by AU. So don't let that confuse you. Okay, you're not always looking for the letters that go with the name. Okay. Second, you're always going to find the atomic number at the top. It could be at the top right, it could be at the top left, or like anywhere up at the top, but it's the largest top number. Okay, and remember the atomic number also represents the number of protons. Next, we have the element name. You can always find right underneath the element symbol, and right below that is the average atomic mass. From periodic to periodic table, they should be pretty much the same atomic mass, no matter what type of periodic table you look at. But sometimes with funky worksheets and things like that, maybe it'll be a decimal point off or something like that. You can always trust the periodic table that I gave you the link to. Okay. And remember, the atomic mass is always equal to the number of protons plus the number of neutrons. Okay. So if I were to be asked a question like on a quiz or a test, how many protons are in calcium? Well, I know just from looking at this that the atomic number is 20. And if I remember from the last lesson, if I just go up here, atomic number is always equal to the number of protons. Okay, so if it asks me that, very quickly I can say 20 because the atomic number is representative of the number of protons. Okay, now I know that the other rule that we learned last time is that all atoms need to be neutral so that they behave. If they're neutral, then there has to be the same number of negatively charged electrons as there are positively charged protons. That is a rule. There has to be the same number. So, if I'm looking at this and I'm asked how many electrons are in calcium, it doesn't blank or like forthrightly say, there's this many electrons, but because I know that the number of protons is always going to be the same number of electrons, then I know if there's 20 protons, there has to be 20 electrons. And then finally, how many neutrons? You can always use this atomic mass rule to figure out how many neutrons. The atomic mass is equal to protons plus neutrons. So if I'm trying to figure out how many neutrons there are, then I plug in my numbers. So for example, the atomic mass of calcium is roughly 40. Okay, so I just used whole numbers here. 40 is equal to 20 protons, because I got that from here, plus blank, or neutrons. Okay, I want to get neutrons by itself, so I've subtracted 20 from both sides. Minus 20, minus 20. There are 20 neutrons. Now, I think I mentioned this in the last video, but there's not always going to be the same number of protons, neutrons, and electrons. Okay, protons and electrons are always going to be the same, but it is rare when you find an element with the same number of neutrons as well. So this is one of those examples. Okay, it came out nice and easy, but there's going to be other examples where the number of neutrons does not equal excuse me, the number of protons. Okay, so moving forward from there, these are two questions I'd like you to answer in your notebooks. What is the difference between atomic mass and the atomic number? That will be a quiz question, so I suggest you practice that now. Remember, atomic mass is equal to the number of protons plus the number of neutrons, whereas the atomic number is just the number of protons. Okay? Yeah. And how are the positive protons held together? The only way that positive protons can stay together in the nucleus is because there are electrons on the outside, right? Just like a magnet, they repel each other, okay? Or they are constantly pulling on each other. So positive protons stay in the nucleus because of the electrons that surround them. That's how it all stays together. Okay. Moving forward, and again, if you at any point think I'm going too fast, please just pause, write it down, and then you can hit play and continue. Now, so we've talked about this. we're going to I've put the rules that we've learned so far on this page so we can see how we can use the periodic table to help us answer some questions quickly. So the rules: atomic number is always equal to the number of protons. I'm always going to find that at the top of the element symbol. The number of neutrons is always going to be the atomic mass minus the number of protons. Okay, so if I have the atomic mass and I have the number of protons here, okay, then I can just go the atomic mass 40.08 minus the number of protons 20 to get the number of neutrons. You can use that you can use that formula for any of these. Okay, so that's one last thing. Now, why does all this matter? Okay, why do we even look at the periodic table? Why do we look at all of these different elements? Well, because elements come together to form molecules. Okay, and the way that they come together is they bond, they hold on to each other. Now, before we can get to bonding, like I said, we have to understand how they hold on to each other. And that's where electron configuration comes into play. Okay. Electron configuration is the arrangement of electrons around a nucleus. You could think of it like the atom's seating chart. Okay. The electron configuration is our prediction for where we can find electrons within that atom. Because remember, if we go back to our notes way back when, over here, we said that we now know that even though we'd love for it to be perfectly circular movements that electrons move around the nucleus in, we know they move around like a cloud. And we can't always predict, well, we can try and predict where we think they're going to be. But remember, they move in waves. Okay, so because we don't know 100% for certain, we come up with electron configurations or a seating chart to kind of track where electrons are. Now, this, remember I said this is important because later on, if we want to figure out how atoms bond to one another to form molecules, we have to understand where the electrons are sitting and where they can connect to other atoms or share electrons or whatever the case might be. Okay, so we're moving with that in mind. This is kind of like the first step in understanding that entire bonding mechanism. Okay, so when learning about electron configuration, there are a bunch of rules. We can't start drawing until we figure out all the rules. So the first couple rules that we talk about are listed here. There's a lot on this page, so we're just going to take it, blurb by blurb. You might want to pause it right here, write it all down, and then we can kind of talk about it and hit play, however you want to do it. Okay, so the first thing, atoms are mostly made of empty space with very dense nucleus in the middle. This is the reason why it's hard to figure out where electrons are, right? I said they're moving in a wave. They move in an electron cloud, excuse me. So it's hard to sometimes find where the electron is. We have to write it out so that we can kind of figure out where they are, okay? And even with that, even if we do write down an electron configuration, electrons are constantly moving, okay? And what that means is that when they're moving, they're gaining or they're losing energy. So we have to predict where the electrons will be around the nucleus at all times. They're constantly moving levels, and so there's just a lot of movement because they're gaining and losing energy. Okay, and you might want to underline that: gaining and losing energy allows them to move. Okay, so where are they moving? It says they're getting closer or further from the nucleus? Well, there's orbitals. So remember I said that we draw this so that we can kind of wrap our minds around this. But every kind of circle here you see around this little blue dot that represents the nucleus is an orbital, okay? And we call each level or each orbit an energy level, okay? There are several names for each energy level, okay? They call it the electron shell, they call it an electron orbit, they call it an electron energy level. These all mean the same thing. One of these circular orbits is a shell, is an energy level, same thing. Please don't get confused if I say orbit or if I say energy level. It means the exact same thing, okay? So, now, each orbit represents an energy level. And if you remember from the notes from last time, I said the closer to the nucleus an electron is, the weaker it is. The further away it is, the stronger it is, because it's like pulling away. Okay? So, orbits that are close to the nucleus have less energy. So, here's the nucleus in blue. And the first little circle around it, that's the first orbit, that's a weak energy level, okay? But as you get further out to the outer ring, okay, if you're further away from the nucleus, you have more energy. Okay, so if I say, for example, right here, which electron has the most energy, purple, green, or red? The answer would be the red electron has the most energy because it is in the outermost orbit or the outermost energy level. It is furthest away from the nucleus, which is in black here. Okay, so the purple one is the weakest. The red one is the strongest. Okay, so that goes with that rule. Further from the nucleus, you have more energy. Closer to the nucleus, you have less energy. Now, next rule. When electrons move up an orbit, they gain energy. Again, moving up means moving away from the nucleus. When an electron moves down or closer to the nucleus, it has less energy. Okay? So those are the kind of rules. I would ask you a question like this maybe on a quiz or a test. Which electron has the most energy? Remember, the further away from the nucleus you get, the more energy you have, the closer, the less energy you have. Now, these diagrams that I've been showing you are called Bohr models. Bohr. Okay, it's named after the last notes we had. There we go. Niels Bohr. He's the one that kind of figured out that energy travels in orbits. Okay, so that's the reason why we named these electron configuration drawings after him. Okay, and he also figured out, again, that electrons that are closer to the nucleus are weaker, electrons that are further away are stronger. Okay, so we call these diagrams Bohr models. And again, here we are. Now, this whole slide, you want to make sure you write down, circle it, highlight it, make sure it's in your notes because you're going to come back to this all the time. Okay, when drawing a Bohr model, we are drawing it with the idea that the electrons are moving in a steady orbit around the nucleus, okay? Now, there's several different rings, right? Here's the nucleus. The first ring can only hold a certain number of electrons. Specifically, I put it here 2, and you'll see it here. For the first shell, it can only hold 2 electrons. So if I'm looking at here, this is the nucleus. I don't write any electrons there. The first shell, which is the first circle, can only hold 2 electrons. I'll show you what that means in a little bit. The second shell can hold 8 electrons. So on the second shell, there can be 8 electrons. Same with the third shell. There can only be 8 electrons. And on the final shell, if needed, there can be 18 electrons. You will not use every shell every single time you draw one of these. Some of them, you'll fill the entire thing up. Others of them, you will not. Okay, so this is just showing you that if you needed 4 rings or 4 energy levels, okay, that you could go up to 18 electrons on the last one. But you really won't need that many for this class. Okay? So again, 2 electrons fit in the first shell, 8 electrons fit on the second shell, 8 electrons fit on the third shell, and 18 electrons fit on the outermost fourth shell. Okay? Next, how do I draw this? So, these are the 3 steps that I've come up with. You're going to have to do a lot more work in between these. So again, I would pause the video and write down these rules and all the side stuff before trying to watch me draw it on the next slide. Okay. So, first rule to creating a Bohr model, find out how many electrons are in that element. Okay, because if you can figure out how many electrons there are, then you can draw it right away. You cannot draw it if you don't know the atomic number. So you're going to go to the periodic table, and let's say I'm drawing nitrogen. Nitrogen has, 7. Nitrogen has an atomic number of 7, which means it has 7 protons, which, because we know the rule, it has to have an equal number of electrons. So therefore, it's going to have 7 electrons. If I were to come back over here, now I know how many electrons there are, and I can start drawing. Okay, so that's step number 1. Find out how many electrons there are in the element being asked about. Once you figure that out by using the atomic number, then you can start drawing. Step 2, you're going to start adding electrons to the ring closest to the nucleus and draw the other electrons on each shell. Okay, I'll show you an example of that. And again, that's going to be, you're starting to put electrons on the ring closest to the nucleus. That would be the first ring for all 3 of these. And then thirdly, you need to fill up each shell. And once you fill up each shell, you need to move on to the next orbit, okay, or the next energy level. So remember the rules. There's only 2 electrons that can fit on the first shell. If there's any left, they have to go on the next shell if they fit. I'll do a bunch of examples of that. So, examples. If I go to the next slide, here we are. Okay, so let's focus in on helium. Okay, you are going to add electrons to your shell and move clockwise. Okay, so for instance, helium, if I look at my periodic table, helium is represented by He. It has an atomic number of 2, so it will have 2 electrons, just like I put here. Okay, now remember the rule. I figured out how many electrons there are. Step 2, I need to add electrons to the ring closest to the nucleus, and then I need to make sure I'm adhering to the shell rule. Okay, so for the first ring, only 2 electrons can fit. So if I go back over here, if I have my little red electrons, helium can hold 2. So I'm going to go clockwise. 1, 2. Click away for a second. Notice that this is the nucleus, so I don't draw anything on there. I found out that there are 2 electrons for helium. They are going to go on the first ring closest to the nucleus. For helium, I only needed 1 ring because it only has 2 electrons. So this is the picture, and I'll move this pink arrow. This is the Bohr model for helium. Completed, this is how it should look. Remember, I went clockwise. 1, 2. I separated them. Let's do it again with one that has more. Boron. Boron, if I look at my periodic table, boron has 5, or an atomic number of 5, which means it has 5 protons. Because it must have an equal number of electrons, boron also has 5 electrons. So going back, boron has 5 electrons. I'm going to add them now. Okay, you start at the first orbital, and it can only fit 2. So I need to go 1 and 2. Okay, that orbital, even though it looks like it has space left, it can only hold 2 electrons in that innermost ring. There's 3 electrons left for boron. So I have to go to the second ring, okay? And let's remind ourselves of how many can fit. There can be 8 electrons in the second ring. Now, I only have 3 electrons left. Just because it's not 8, that doesn't matter, okay? That's totally fine because we're just, we don't have to fill it up every time. For boron, it only has 5 electrons, and so we only have 3 left. That's fine. It'll fit in the second ring. So just like the rule says, add electrons clockwise. So this is electron number 3 for boron, electron number 4 for boron, and electron number 5 for boron. And notice all 3 of those are on the second ring. We could have fit 8 electrons on this outer ring, but we didn't need it because boron only has 5 electrons. 2 in the first ring, 3 in the second ring. Okay. For phosphorus, phosphorus has 15 electrons. Again, I'm going to find it over here. Phosphorus is its chemical symbol is P for phosphorus, and it has an atomic number of 15, meaning it has 15 protons, which means it has 15 electrons. So going over here, since we know that information, we're going to start in the innermost ring, and it can only carry 2. So out of 15 electrons, we can only put 2 in this inner one. 1, and then I'm going to move clockwise and put a second one, 2. Now I have 13 more electrons I need to place on here. So I'm going to go to the second ring, and I know that it can hold 8 electrons. I will need all 8 spaces this time. So 1, 2, then I'm going to take another electron, the second ring, 3, 4, again moving clockwise, 5, moving clockwise, 6, 1, 2, 3, 4. Now I've only put 4. Now I can double up and put a second one. So there we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, notice, I have 8 electrons in this second ring. 1, 2 in the first one, and then 2, 4, 6, 8 on the second ring. That second ring is now full. I can't put any more on there, but phosphorus has 15 electrons, right? If I have 10 electrons already on here, I have 5 more I need to add to the next ring. So this is the first ring, there's 2. The second ring, there's 8. Let me check my rules. The third ring can also have 8 electrons. I don't need that many, but I can fit them there. So I'm going to add the rest of the electrons that I need to. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, clockwise, 11, 12, 13, 14, and I need to put it one more, 15. And it's right there. I don't know if you can see that. All on the outer ring. There's 15 total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 electrons on this Bohr model to represent phosphorus. Anytime I see a Bohr model with 15 electrons drawn like this, I know it represents phosphorus. Okay, if you're having trouble with this, practice these over and over again, but we're going to have lots of practice on the homework as well. Same concept. The homework looks like this. You're going to be given the number of rings needed. It's going to ask you to draw in. So I'm just using a Word document and I'm going to draw in, let's see what color. There we go. I'm going to draw in the electrons on here. So hydrogen, if I look at my periodic table, hydrogen has 1 electron, so that's super easy. Okay, if I go to my homework, hydrogen, I could type that in a minute, but hydrogen, here's the nucleus, here's my first ring, and I'm just going to draw one. Whoa, that looks ugly. Hold on. One little, there we go. Oh my goodness, I cannot draw it. Hold on. Ay, ay, ay. Let's see here. That doesn't look good either. There we go. 1 electron. And then I'm going to go back to my mouse and type in, this is hydrogen. The atomic number is 1. I only used 1 orbital or 1 shell. And then the electron configuration is your picture. So you've drawn the electron configuration here. For the next one, this is helium. He stands for helium. I can figure that out by going to my periodic table. Helium has an atomic number of 2. So I'm going to write that in. Element helium. And if I'm going to use my drawing tool, I'm going to go 1. Let's make a little circle there. And then 2. Okay. And so the atomic number, let's see. Atomic number from the periodic table was 2, and I only used 1 shell. Boom. So this is how you're going to do your homework. You're just drawing the Bohr model for each of these. It takes a lot of work, especially as you get into the bigger ones. Okay, but you'll be fine. It'll work out. Okay. So going back over here, so now we figured out how to draw a Bohr model. The other types of models that we use are called Lewis dot diagrams, and these are special diagrams because they only show the valence electrons in the outermost, and valence electrons are electrons that are only in the outermost shell of your diagram. So for instance, we just made this Bohr model for phosphorus, right? We just did this right over here. Okay, so I copy pasted that and I put it here. This is the Bohr model, but if I wanted to write the Lewis dot diagram, I would draw the Bohr model and then I would find out where are my valence electrons. Valence electrons are the most important electrons in the configuration. Those are the ones on whatever is the outermost shell. So for example, for phosphorus, this one has 1, 2, 3, 4, 5 valence electrons. So I only highlighted in purple the ones on the outermost rim. Okay? Those are my valence electrons for phosphorus. That might not be the case for any other electron, but we have 5 on the outside for phosphorus. Notice in the first shell I had 2, 1, 2. In the second shell there was 8, 2, 4, 6, 8. In the third shell, 1, 2, 3, 4, 5. There's 5 valence electrons for phosphorus. So if I were to draw a Lewis dot diagram here, all you have to do is number 1, here's the little rules to the side here. Write the element symbol. So for phosphorus, if I look at the periodic table, phosphorus is symbolized by P. So I put a P here. Then you identify how many valence electrons there are. For phosphorus, there are 5. So I have 5, 1, 2, 3, 4, 5. And then you're going to draw it just like how you did, or draw it clockwise, just like how you made the Bohr model. So 1, 2, my mouse will work for me, 3, 4, and then now we're going to double up, and 5. It's okay here, you don't have to make like a new ring, okay? You just keep filling it in all around the letter. So this is the Lewis dot diagram for phosphorus. Over here we have the Bohr diagram. Here we have the Lewis dot diagram that only shows the valence electrons. This is important, and the reason why I said valence electrons are the most important is because they show us how that element is going to behave. So its valence electrons are the ones that can bond to other elements. So if I wanted to connect phosphorus to nitrogen, or phosphorus to carbon, or phosphorus to anything else, oxygen or whatever, then I can only use the valence electrons to connect to another element. Okay? So that's why we always identify the valence electrons on or for an element, because that's going to tell us how that element is going to behave. Okay? You're going to need more practice with this. We'll get more practice later on. Right now, I want you to master drawing Bohr models. And then from a Bohr model, I want you to be able to identify the outermost ring and how many valence electrons there are, and then be able to draw a Lewis dot diagram. Okay, so let's try one that we haven't seen before. This one is sulfur. Okay, sulfur is represented by S on the periodic table. Okay, here it is, sulfur. It has an atomic number of 16, which means that it will have 16 protons, which means that it will have 16 electrons. So I wrote that here. Okay. Oops, sorry. I'm not sure what happened there. So since it has 16 electrons, okay, we're going to draw these here. I don't know why I have that to the side, but here we are. Okay, so sulfur. We're going to start out with the rule. The first orbital can only hold 2 electrons. So number 1, number 2. Then we're going to move to the second shell here. Okay, 3 at the top here. 4 going clockwise. 5 down here at the bottom. Same line. 6. And then 7. 8. 9. And 10. And the reason I have the other ones purple is because I want us to remember that those are valence electrons. I have 10 electrons on the board out of 16, so I need to add 11, 12, 13, 14, 15, and 16. So total, if you start from the very beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've drawn in all the electrons. The purple ones represent valence electrons because they are in the outermost orbital or the outermost shell. If they have 6 valence electrons, then when I draw the Lewis dot diagram, I will have 6 electrons only, because I'm only showing the valence electrons. 1, 2, 3, 4, 5, and 6. And if it makes it easier to understand for you, because I'm color coding, okay, these are only valence electrons that I'm drawing. So these should be purple. Purple. They should all be purple. Okay, and that is sulfur. Remember, we draw the valence electrons because that shows us how the sulfur atom is going to behave when it's around others, where it can bond to other elements. Final example that I'm going to do is kind of starting to show you the process of how different atoms bond together, forming a molecule or forming a new substance. Okay, so for example, C stands for carbon. Carbon on the periodic table says it has 6 electrons. So I'm going to draw the Bohr model for carbon. 1, 2, go into the second orbital. 3, 4, 5, and 6. I didn't need to go very far. Okay. If I draw the Lewis dot diagram, I will only have 4 electrons around carbon, and it'll look like this. Okay. Now, hydrogen has 1 electron. Again, going to the periodic table, hydrogen, 1 electron. So I'm going to put that on the Bohr diagram. Here's my 2 Bohr diagrams. Hydrogen has 1 valence electron. Again, it only has 1, so its outer shell is that 1. Okay, so I should probably write that in. 1 valence electron. And if I go over here, here's my hydrogen. And if I'm drawing the Lewis dot diagram, it's just going to look like this. Boom. That's it. Now, if I have hydrogen and carbon in the same area, I put this little square deal because carbon will behave in a way that it's going to share its electron with hydrogen. Okay? They're going to hold on to each other. And we'll talk more about that later on. But when they hold on to each other, they start to form something new, a bond. They start to form a molecule. This can turn into sugar. This can turn into different types of things. It can turn into glucose, which is sugar. It can turn into fructose. It could turn into a bunch of different types of molecules when they share electrons or when they borrow electrons. We'll learn more about that at a later lesson. Right now, what I want you to see is we went through this entire process of one, being able to read the periodic table, to step two, understanding that we need to draw an electron configuration so that we can identify how atoms are going to behave in the hopes that we can figure out how they bond to one another. We figured out that the first step in doing this is drawing a Bohr model, and we have a few rules that we have to adhere to in order to draw them properly. We practiced drawing the Bohr models, okay? We then said that that's not the last thing we need to do because we want to highlight valence electrons, or electrons on the outermost shell of each atom. And we do that because those valence electrons are going to teach us how those elements behave, or bond, how they bond specifically. We did another practice problem going from the Bohr model to the Lewis dot diagram. And finally, we're here where if we take two different elements that are very much different from each other and we have them in the same vicinity and we know what their valence electrons are, we can better understand how they might behave, how they might bond, what they might connect to, and um, how they might behave after they've connected as well. So that is today's lesson. You're going to get a lot of practice with that here. Okay. It might seem tedious, it might seem like a lot of work, but what you're going to do is you're going to draw the Bohr model for each element. Again, the element symbol is at the top. You have to figure out what element it is, what its atomic number is, draw the Bohr model, and then tell me how many shells you used. Don't look at the electron configuration. I'm counting that as your drawing. Okay? So you're going to go all the way to calcium. I highly suggest doing this in order because you'll see that there is a pattern to all of this. So I would go helium all the way to boron, boron to carbon, carbon to neon, neon to sodium, sodium to phosphorus, phosphorus to sulfur, sulfur to calcium. And yeah, if you need help, please keep rewatching this video. I will be there on Wednesday to help out, but I won't be there any other day after that. Love and appreciate you guys. Have a fantastic rest of your day. Please upload a picture of these notes for credit. And yeah, have a great day. Bye, guys.